Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Picture a chilled chamber, wires draped like ivy over a wafer-thin chip, and a steady ping from the cryostat, tracking a temperature colder than deep space. Engineers huddle around monitors as they press run. Inside that chip, 105 superconducting qubits fall into perfect quantum choreography. 20 minutes later, numbers scroll across the screen. Solution found. The same calculation would leave today's fastest supercomputer grinding for millions of years and gulping more energy than the planet uses in a day. The lab erupts in a quiet, astonished cheer. A milestone in quantum computing has just clicked into place. Moments later, headlines note a twist. A classical supercomputer tackled a simplified slice of the problem in 2 hours, fast enough to stir debate about what quantum advantage really means. Yet the core result stands. For a fully specified benchmark, quantum speed soared past any feasible classical timeline. Energy use plummeted. Error correction routines, once the Achilles heel, cruised below threshold, thanks to clever qubit layouts and real-time feedback. Now, let's lean forward and ask, how could breakthroughs like this reshape space travel? Start with trajectory design. Plotting an interplanetary route is already an optimization jungle of gravity assists, fuel constraints, and time windows. Add autonomous swarms of hundreds of probes, each with variable thrust profiles, and the math explodes into a combinatorial labyrinth. A quantum optimizer could slash weeks of ground station crunching to minutes on board, letting a flotilla tweak its flight paths mid-journey as planetary positions, solar storms, or micrometeoroid densities shift. Less fuel, tighter arrival windows, richer science return. They mixed materials. High-speed travel punishes hulls with radiation and dust impacts. Discovering ultralight alloys or metamaterials that self-heal under cosmic rays demands simulating quantum interactions among thousands of atoms. Precisely the regime where classical methods show quantum computers excel. At these electronic structure crunches, they could iterate new space-grade polymers or superconducting wires in silica overnight, then feed blueprints to orbital microfactories. Now, picture fusion. Compact fusion drives promise continuous thrust and month-long Mars transits. But taming plasma turbulence still strains supercomputers. Quantum processors can model magnetized plasmas at the particle level, mapping instabilities before they erupt. Each simulated shot refines coil geometry and fuel mix, speeding the march from prototype to flight-ready reactor. Navigation too. Deep space probes rely on Earth-based antennas for precise timing. With quantum-level clock synchronization, a spacecraft cluster could cross-calibrate via entangled photons, holding picosecond accuracy across billions of kilometers. Combine that with quantum-secure links, and mission data stays immune to spoofing, even in contested cis-lunar space. Then there's Onboard AI. A crewed Jupiter expedition will bristle with sensors, life support analytics, and robotic assistance. Training large models in flight is impossible today. The data must beam home. A compact cryogenic quantum coprocessor could refine medical imaging algorithms or anomaly detectors locally, adapting to unknown Jovian moon environments in real time and cutting the radio lag out of critical decisions. Move forward a century. Terraforming engineers seed Venusian clouds with autonomous aerostats. Each balloon carries a ruggedized quantum chip cooled by radiators fanned out like petals. The fleet cooperatively solves atmospheric chemistry, solar mirror alignment, and weather pattern predictions every few minutes, nudging a runaway greenhouse toward habitability. Or leap farther. An interstellar probe, riding a laser, sail hits a dust storm in the Kuiper Gap. Onboard quantum solvers ingest real-time dust impact maps and retask swarm drones to fly ahead, ablating larger grains with micro lasers. Classical algorithms would miss the window. Quantum crunching keeps the sail intact and the mission alive. Even fundamental physics. During cruise, the probe deploys atom interferometers to scan spacetime for tiny ripples. Quantum computers onboard sift petabytes of phase shift data, searching for hints of dark matter fields or extra dimensions. Discovery happens on the fly, freeing humanity from light-hour delays. There are hurdles. Quantum chips prefer -269-degree baths. Not easy on a sun-scorched orbiter. Engineers are exploring diamond spin and photonic qubits that thrive at room temperature, opening doors to satellite payloads. Error correction overhead still bites. But hybrid schemes hand classical processors the noisy bits, while quantum cores tackle only the entangled heart of each computation. Cost curves echo early microchips. Today's million-dollar fridge racks will condense to suitcase cryo modules, then to alloyed sapphire wafers, chilled by passive radiators. By the time fusion tugs clear Earth orbit, a quantum CPU may sit beside the reactor controller like any other circuit board. Ultimately, quantum milestones fold into a larger pattern. Every leap in computation has unlocked a new transport frontier. Steam engines followed thermodynamic theory. Rockets followed numerical integrators. Reusable boosters rose with real-time guidance chips. Quantum leaps will likely usher in propulsion regimes that seem mythical now. Warp metric optimizers, Casimir dry field solvers, negative mass stability maps. Each requires math classical silicon can't touch, but quantum entanglement can. So while experts debate benchmarks, a more exciting contest has begun. Weaving these fragile qubits into spacecraft blueprints, the processor that just humbled a classical behemoth is more than a lab trophy. It is the prototype navigator, the materials oracle, the fusion whisperer of voyages yet unflown. And somewhere out in that cryostat, qubits still hum in coherent superposition. Tiny choreographers writing the equations of tomorrow's Odysseys. One entangled dance at a time.